Okay, so this is the first of probably a lot of videos about chemical reactions because we're going to go into a lot of different details and there's a lot of things that you have to remember as we continue. So the first ones that we're going to talk about are synthesis and decomposition. So the first thing that you want to do when approaching a chemical reaction is identify what type of reaction are we dealing with. And you can do that by looking at the reactants. The reactants will always be on the left side of the yield sign. That is the yield sign. This arrow, that's saying that our reactants on the left, can't spell, yield or produce our products. Your products will always be on the right. And so a lot of times you will be asked to predict what type of product you have. So to predict the product, you have to look at the reactants first. So we're going to analyze the reactants. So as you can see on number 1, we have lithium plus sulfur. The plus sign indicates that these two are separate from each other. So you have to think that we have like two, wrong color. We have like two containers, one of lithium and one of sulfur, just for simplicity. And we are going to add them together. So our arrow is basically us saying that we're going to put lithium in here and sulfur in here, and let's see what we produce on the other side. So to figure out what we're producing, we have to look at what we're putting in, and we have to ask ourselves, is it elements and elements, or is it elements and compounds? And there's a whole list that we're going to talk about. But this one is specifically a synthesis reaction. You can tell that because the two things being added together are lithium and sulfur. Lithium is just an element, and sulfur is just an element. So when we take element plus element, we are going to synthesize a compound. So anytime you say element plus element, this is a synthesis reaction. Okay? So in synthesis reactions, you are just going to put the two elements together. So let me take the two elements, lithium and sulfur, Li and S. You're just going to put them together. Now, it is key that you remember that compounds have charges. Sorry, I'm writing awfully tonight. I'm so sorry. So let's think about the charge on both lithium and sulfur. And since now they are pushed together like this, this is now a compound. I'm sorry, I skipped a step. Let me remember to go back. We want to make the product using words first, just using our naming rules. So we're going to say that our product is lithium sulfide. Remember, that is how you create a compound. You use your metal and you just put it, and then your non-metal, you will change the ending to "ide." So lithium and sulfide. You don't change the ending if you're dealing with the polyatomic, but sulfur and lithium are both monoatomic. Okay, so now we can actually write out our problem. Li plus S makes LiS. And remember, we have to do the charges. That's what I was talking about. Sorry, my dogs are making lots of noises. Okay, so Li, lithium is on group 1, so it will have a +1 charge. Sulfur is on group 16, so it will have a -2 charge. So 1 and 2 does not match. So to make the charges match, remember we have to lasso. So I'm going to bring this 2 down to the bottom of lithium and the 1 to the bottom of S. Okay, so now it matches. So any reaction, we have to balance, okay? So the last step of any reaction is to balance the equation. So our equation is not equal at the moment. So what I mean by that is count the number of lithiums on each side. So on the reactant side, this side, I have 1 lithium. So I'm going to put lithium under the arrow and just put 1 on the reactant side. Now on my product side, I have a 2 right here. So I have 2 lithiums on the product side. So let's do the same thing to the sulfurs. So I'm going to put the sulfur here. I'm sorry, I'm running out of room. On the reactant side, I have 1 sulfur, so I'm going to write a 1. On the product side, I have 1 sulfur, so I'm going to write a 1. So let's analyze our list. The lithium is 1 and 2, so that is not equal. So we have to use coefficients to make them equal. A coefficient is a big number that goes in front of the compound or the element. So for lithium, I have 1 on the reactant side and 2 on the product side. So that means that I obviously need to increase the 1 to a 2. How do I do that? I go to the lithium and I do not put a 2 there. Okay, I cannot change those numbers at the bottom. The only way to add more lithiums is to put a 2 in front. Okay, so now I have 2 lithiums on the reactant side, 2 lithiums on the product side. Let's look at our sulfurs. I have 1 sulfur on the reactant side and I have 1 sulfur on the product side. So the sulfur is balanced, the lithium is balanced. We have our final equation right here. Hold on, let me see if I can do it. This is our final equation. Okay, so you can continue to do that for all of the synthesis reactions. And so I can tell you that all of these will be synthesis reactions because each of them, you have an element plus an element, element plus an element, element plus element, element plus element. And remember, a synthesis reaction is when you are putting 2 elements together. You will remember to balance the charges in the compound and then balance the equation itself using coefficients. So for decomposition reactions, these are our second types of reactions. You will always start your reactant with a compound and then you will immediately have an arrow. So the only thing that is on the reactant side is a compound. Now, you can have different classifications of decomposition reactions. We can have a monoatomic, which just means that your cation, your metal, and your anion, your nonmetal, are both monoatomic, okay? You can figure that out by looking at the anion and checking if it ends in "ide." More than likely, if it ends in "ide," it is going to be monoatomic. The only exception would be a hydroxide because we have a rule for that down here. Okay, so for monoatomic reactions, you are just going to break the 2 pieces apart and then balance the equation. The only thing that you have to watch out for here are diatomic elements. Diatomic elements mean that you will never see these elements by themselves. It's hydrogen, oxygen, nitrogen, and I'm forgetting one. Okay, I'm forgetting one. I know I am. Hold on. Forgetting a lot. Okay, fluorine, chlorine, bromine, or iodine. Those are diatomic reactions, meaning if they are not already a part of a compound, okay, if they are in a compound, then this does not apply. But if they are not a part of a compound, meaning they are just sitting by themselves, they will never be alone. So there will always be 2 of them. So the only thing you have to watch out for monoatomic are the diatomic elements. So if you produce a hydrogen or produce an oxygen, you have to make sure that they're not alone. They have some type of partner. Okay, you can also have a chlorate type of decomposition. This means that the compound will end with a chlorate. Every single time you will create a metal chloride. So whatever metal was with the chlorate, you will on the product side put it with a chloride, which is just a chlorine. And then you will always make an oxygen. So you have to make sure that you make that metal chloride by using the charge that was on the metal in the reactant, and then create the compound by using a lasso technique, then go back and balance the equation. You can also have a carbonate decomposition reaction, which means that you will have a, I'm sorry, this is wrong. Means that your anion will be a carbonate. For these, you will make a metal, the metal that was with the carbonate. On the product side, you will take that metal and make a metal oxide and a carbon dioxide every single time. And make sure that for this metal that we got from the reactant side, that you bring its charge and you make that lassoed compound correct. And then just remember to balance the equation. I mentioned this a second ago, but you also have a hydroxide. This is a decomposition in which the compound on the reactant side is a hydroxide. You will create a metal oxide. So whatever metal was with the hydroxide on the reactant side, you will bring that metal over and put it with oxygen. And you will also remember to bring the charge and build the reaction, build the compound using that charge, and then lasso, making the charges balance. You will make a metal oxide and water every time. Balance the equation. The last one is an acid. So to figure out if you are doing an acid decomposition, you will only see an acid and then the arrow. So you'll see some type of acid. Remember, acid has H in front. And then on the reactant, on the product side, you will make the non-metal oxide and water. Now for this one, you can't just bring the charge over from the reactant side. So you have to have specific instructions on what non-metal oxide to make. But once you do, you will just balance the equation. So let's go up here and look at a few. So our first one is potassium nitride. I want a different color. Potassium nitride. So I noticed that this is a compound because there is not a plus sign right there. So that means that we have compound arrow. So that means that we're dealing with a decomposition reaction. So for decomposition reactions, we have to look at our anion and determine, is this mono, is it a chlorate, is it a carbonate, is it hydroxide, or is it an acid? Well, it says nitride. And remember, if it ends in "ide," it is going to be mono. Our only exception was the hydroxide. So the monoatomic, your instructions are just to break the two pieces apart and balance. So let's do that. We have potassium nitride. So I'm going to take potassium and then say plus nitrogen. Now notice the changing of nitride to nitrogen, because nitrogen, when it is not a part of a compound, you don't keep that name. You change it back to its like original name. So nitride would turn into nitrogen. Okay, let's get rid of some of this so I can finish it out. So right here, I'm just going to change this into a formula. So potassium is K, nitride comes from nitrogen, which is N. Remember to bring charges. K is +1, N is -3. So then just balance by using our lasso rule. So the 3 goes here and the 1 goes there. The reason we put charges on this one is because this is a compound. Okay, compounds, you have to use the charge to balance. Now on our product side, we don't have compounds. This is an element plus an element. I misspelled that, but whatever. So they will not have charges. So we're just going to write K plus N. And remember, I told you to watch out for diatomic elements. N is diatomic. So meaning you have to look at it and say, does it have a partner? No, it is N by itself. So you have to give it a partner. So you just put a 2 down there to indicate that now the nitrogen has another nitrogen. Okay, so we have broken our compound into 2 pieces. We have balanced our compound and we have checked for diatomics. The last thing we need to do is just balance the equation. So let me use a different color. I'm going to put the 2 elements underneath the arrow sign and then just count how many I have on either side. So on my reactant side, I have 3 potassiums, so I'm going to write a 3. On my product side, I have 1 K or 1 potassium, so I'm going to write a 1. On my reactant side for nitrogen, I have 1, so I'm going to put a 1. And on my product side, I have 2, so I'm going to put a 2. Now, I am going to work from the top of this list downward, balancing them out by using coefficients. Remember, coefficients go in front of the word, or in front of the symbol. Okay, so I have 3 potassiums on this side, and I have 1 on this side. Well, that does not equal, so I need to change my 1. The easiest way to make it equal 3 is to put a 3 in front of the K, and now I have 3 potassiums. I have for my nitrogen, I have a 1 and a 2. So this 1 needs to change, needs to get higher. The easiest way is to put a 2. Now the 2 has to go in front of the whole compound. So now I have 2 nitrogens, but it also applies to the potassium. I have 2 times 3. So now I have not 3, I have 6 total potassiums. So now I have to rework down this list from top to bottom because now they don't balance. So I'm going to say I have 6 and I have 3. So I'm just going to change this. I'm going to go back and I'm going to look at where this came from. I have a K. I don't want that 3 anymore, so I'm going to take it away. What needs to go in this place? Oops. What needs to go in this place to make this K equal to this K? Well, this K is a 6, so this side has to be a 6. So that changed it to 6. So you may ask, what is right here? That's an understood 1. There's no need in writing it. So now let's just make sure that everything balances by rechecking through my whole equation. I have 2 K3Ns. So that means I have 2 of these compounds. Now let me prove to you that that means I have 6 potassiums. If I have 2 of these compounds, K3N, that means I have K3N, K3N. How many total potassiums do I have? 3 and 3, so I have 6. How many nitrogens do I have? 1 and 1, so that makes 2. You don't have to do this big drawing every time. Instead, you can just multiply the coefficient by the subscript. So I'm just going to say I have 2 of these times 3 of these, so that makes 6. Clean that up. Okay, now how many K's do I have on the product side? I put a 6 there. 6 times the 1 gives me 6. All right, so my K is balanced. Let's look at the nitrogen again. 2 of these. 2 times 1 makes 2 nitrogens. 1, that understood 1, times 2 makes 2 nitrogens. So K is balanced, N is balanced. My equation is finished. Okay, let me do this copper 3 carbonate for you, and then we can analyze the rest in class. So copper 3 carbonate. Notice that this is a compound, because there is no plus sign between the copper and the carbonate. So this is a decomposition reaction. We have to go down here and figure out what kind it is. Well, it says carbonate, so that means it is a carbonate. So that means that our product will be metal oxide and carbon dioxide. So go up here, find your metal. The metal is copper. So I'm going to make copper. Let me use a different color. Copper. Remember to bring the 3. Oxide. Remember, that's what it told us to do. It told us right here to make a metal oxide. So I took my metal, which was copper. I brought its charge with it, and then I put the oxide with it. And we will get CO2. So I'm going to also put plus CO2. Let me write it out since I'm in the word formula. Carbon dioxide. Okay, so now I can transfer the words to a formula. Copper 3 means the charge. Carbonate is CO3 minus 2. Now don't forget 3 and 2 don't balance, so you need to lasso the charges. Okay, yields, again, copper 3, Cu plus 3. Oxide means we have oxygen. And don't forget, oxygen in a compound has a minus 2 charge. Okay, so these charges do not balance, so I have to lasso. Moving on, carbon dioxide is CO2. No need to deal with the charges because carbon dioxide tells me exactly what I need. 1 carbon, 2 oxides. Okay, so we have built the compound. Now we just need to make sure that the compound will balance. So I'm going to write CuCO. Those are the elements that I have in this formula. A good key is to always put oxygen last. Notice that I put oxygen at the very end of my list. The reason for that is because oxygen is in many places. It's here and here. So I'm just not going to deal with it till the very end. Okay, so now let's count up how many coppers I have. I have 2 right here, 2 coppers and nothing in front yet. So I have a total of 2. On my product side, I have a 2 right here for the copper and nothing in front. So I have a 2. Now for my carbons, I have a C, but notice this 3 out front. Remember the 3 applies to the entire compound. So the 3 applies to the C. So I have 3 carbons. Now on my product side, I don't have any C's here, but I have a C in the carbon dioxide, and I have 1 of them. So I'm just going to put 1. Now let's count up all the oxygens. I have O3, so I have 3 there, but I have 3 of them. So multiply those numbers together, and I have 9. Look on your product side, you have 3 here, plus the 2. So I have a 3 plus 2 gives me a 5. Okay, so work down this list, down the list, starting at the top and getting them equal as you go down. So our first ones are equal, 2 and 2, that's equal, so we're good. Now the 3 and the 1 is not equal, so I need to change my product side. So go find where the carbon is, it's right here. What can I put out front to make it equal to the 3 on the previous side? Well, it's 1, so I can say 1 times 3 would give me 3. But what does that also change? Do you see that the 3 applies to the carbon and the oxygen? So that then changes this oxygen to a 6. So now I have 3 here and 6 there. So it's no longer 5 oxygens on the product side. It is now 9. Which really works out considering I have 9 on the reactant side. That's why we don't deal with oxygens till the end, because most of the time, if everything else balances, you can just count up your oxygens and they will probably work out. If they don't, then I recommend starting it back at the top. Okay, so just to summarize what we did, we noticed that this was a compound, and so we figured out that it had to be a decomposition reaction, and we classified it based off of this anion, a carbonate. Carbonates will always, always, always make an oxide with the metal and a carbon dioxide. So you don't have to think about what to put on the product side. Just go ahead and bring this metal over, bring its charge, and put it with an oxide. And then add carbon dioxide. So that's what I did. I said copper 2 carbonate. Remember, I balanced my charges. Yields copper 3 carbonate. Yields copper 3 oxide plus carbon dioxide. Then I tallied up all of my elements, copper, carbon, oxygen, leaving oxygen for last. I said I have 2 coppers, 2 coppers. I had 3 carbons, but I only had 1 carbon, so I put a 3 in front. That changed the carbon to 3. But it also applies to the entire compound, which has an oxygen in it. So that meant that my total oxygen on my product side was now 3 here plus 3 times 2. 3 times 2 is 6, plus 3 gives me a 9. So I said 3 plus 6 gives me 9. While on my reactant side, I had 3 times the 3 in here, so I had 9 there as well. So everything balances out, and this is my final compound or my final reaction. This is going to take a lot of time, a lot of trial and error. So don't get discouraged quite yet, or ever really, but we're going to do a lot of these and work together enough that it should become second nature to just finish out these reactions and lasso the charges and balance the equations.